Welcome to AP Physics Made Easy. We're starting our AP school year, and if you're starting to figure out that it's a little bit challenging, join the club. That's what I'm here for. My name is Eric Sampson. I'm going to try to help make this easy for you, okay? So let's get started on a really important topic today, acceleration. So acceleration is basically the rate at which an object changes its velocity, right? So let's just start with a very simple one. I've got a car here that's at rest. At time t equals 0, it's not moving. So then the light turns green. Well, what happens is, 1 second later, at t equals 1 second, the car is now going 5 meters per second, as you can tell by my cool little symbols here. And then at t equals 2 seconds, it's going 10. And see, it's going faster. And then at t equals 3, it's going 15, even faster. So I think you've probably already figured out what its rate of acceleration is, but let's just walk our way through this here. So the equation we're going to use is this one here. We say that acceleration is equal to the change in velocity divided by the amount of time it took to make that change happen. Now, remember, delta always means final minus initial. So let's expand this then to just say final velocity minus initial velocity divided by the time needed to implement that change. That's what acceleration is. So in this case here, my final velocity was positive 15 meters per second. My initial velocity was 0. And it took 3 seconds to make that change happen. And so I get an acceleration of 5 meters per second per second. Now, at first that seems kind of weird, meters per second, but if you think about it, what that means is every second you're going to go 5 meters per second faster in the positive direction, or you're going to change your speed, your velocity, by 5 meters per second every second in the positive direction. If you live in America, think about miles per hour. My car is going to go 5 miles per hour faster every second. All right, so it makes sense, meters per second, but usually we're going to express it this way. We're going to say meters per second squared. Mathematically, it's the same thing, just easier to write and work with, so we're going to use that so we don't have a complex fraction all the time. Okay, well, let's try this. I've got a car, instead of starting at 0, it's starting at 10 meters per second at time t equals 0. And let's just see what happens to this car over the next few seconds. So at t equals 5 seconds, the car is still going 10 meters per second. But at t equals 6 seconds, the car's velocity is now 5 meters per second in the positive direction. And at t equals 7 seconds, the car has come to a stop. So let's just apply this acceleration equation to two different parts of this trip. So for the first part, from time t equals 0 to t equals 5 seconds, we see there hasn't been any change in its velocity. So what you'll find is then, mathematically, since acceleration is delta v over delta t, and delta is final minus initial, if I say 10 minus 10, I get 0 in the numerator, so obviously my acceleration is 0 meters per second squared. I want to point something out here, though. It is a fairly common misconception that students have that if an object is moving fast, it's accelerating. So you can have a very large velocity and have an acceleration of 0 if you're not changing your velocity. But also, and more importantly, you can have an object who temporarily has a velocity of 0 at the moment you look at it, who has a very large acceleration. So please don't try to link those two together. They're different aspects of motion. Let's look at the last part of its motions. From time t equals 5 seconds to t equals 7 seconds, let's see what the acceleration is. So I'm going to use the same equation, final minus initial, so my final is 0. My initial was positive 10, so that gives me negative 10. Now here's why we always write it as delta t, because I'm not going to use 7 seconds, because I'm only looking at it in this time period here. So how much did the time change? So delta just means final minus initial, so I take my final time, which is 7, minus my initial time, which is 5. When I put this all in here, I get the acceleration is negative 5 meters per second squared. The object's velocity is in the positive direction, but it's slowing down, and that tells me it's a negative acceleration. So this brings us to an important concept, which is that acceleration, like velocity, is a vector quantity, and that means the direction is very much something that matters. So let's just look at a couple scenarios here. I have a car traveling to the right, positive direction at 10 meters per second squared at time t equals 0. And now I see 4 seconds later, it's going even faster in the positive direction. Well, the thing is, if you're moving in the positive direction and you're speeding up in the positive direction, then you have a positive acceleration. The acceleration vector points in the same direction as the velocity vector. And we can show that mathematically by saying, well, final minus initial is going to be 30 minus 10, over 4, which gives me positive 5 meters per second per second. I don't know why I didn't put meters per second squared. What was I thinking? But I say I get a positive value, it's speed up in the positive direction. Now, here I have an object that's going 20 meters per second in the negative direction, that's its velocity vector, and 3 seconds later is going 50 meters per second, also in the negative direction. So it's speeding up in the negative direction. Well, if you're speeding up in the negative direction, that means your acceleration is negative. So a negative acceleration does not mean slowing down. It means your acceleration vector is pointing in the negative direction. And so if we solve this mathematically using the acceleration equation, my final velocity is negative 50, my initial velocity is negative 20, and the time is 3. And when I work this out, I'm going to get negative 10 meters per second squared, which is pretty fast acceleration, but it must be an awesome car. Just look at it. All right, well, let's keep going then. How about this? I have a car that's initially traveling 30 meters per second in the positive direction, but then 4 seconds later, it's only going 10 meters per second in the positive direction. So it's slowing down in the positive direction. Well, that means it has a negative acceleration. And we can see that mathematically by taking the final minus initial. 10 minus 30, that's negative 20 divided by 5, gives me negative 4 meters per second squared. So if you're slowing down in the positive direction, then you have a negative acceleration. Now, so I'm going to do the same thing the other way. You see where we're going. I start off at 50 meters per second in the negative direction, and I end up only going 20 meters. So I'm slowing down in the negative direction. Slowing down in the negative direction means you have a positive acceleration. And we can show that mathematically by saying negative 20 minus negative 50 divided by the time gives me positive 3 meters per second squared. Now let's take a look at this. I'm looking down at an object like from drone footage, okay? So I have this car that's traveling north at 20 meters per second. But this car is on cruise control. And what that tells me is that the magnitude of its velocity is going to stay 20 meters per second. Its speed is never going to change as long as we keep that cruise control on. But look what happens. The driver decides, I want to be on this road over here. So the driver turns onto a highway that's going now to the west. Now, still on cruise control. So the entire time between here and here, this speedometer reading on the car said 20 meters per second. The thing is, this object did accelerate, even though its speed stayed at constant. So you can travel at a constant speed and be accelerating. And the reason is because velocity is a vector quantity. And that means it has a directional component. So 20 meters per second north is not the same thing as 20 meters per second west. So to implement that change, we had to have an acceleration. This is called centripetal acceleration. We'll look at it at a future unit, but just know you don't have to change your speed to accelerate. You just have to change your velocity vector. So just looking at this picture, you probably already know what this is about. This is the Leaning Tower of Pisa, a very iconic piece of architecture in Italy. And there's a story associated with it. Whether this story is true or not is a matter of debate. But here's the idea. There was this young man in the 1500s named Galileo Galilei who essentially started the whole process of approaching science through experimentation. He came up with most of the equations we're going to look at in this unit, in Unit 1 of Kinematics. But basically, he did some experiments on his own that showed him that this old idea was wrong. And the old idea was that heavier objects fall to the ground faster than lighter objects. And this is probably because people, we've noticed that if you drop like a feather, it lands, it takes it longer to reach the ground than it does when you drop a rock. And so people go, see, the rock's heavier, it got there first. Turns out it's a little more complicated than that. And what he realized was, no, actually, if you drop a very large rock and a very small rock, this is not what happens, although everybody thought it was. So the story goes, he gathered a crowd at the bottom of the Leaning Tower. He dropped two objects, and they both hit at the same time. And rather than everybody saying, oh, you just proved that Aristotle was wrong when he taught us these ideas, they said, you bewitched the heavy one to fall slower than it was supposed to. That's how the story goes, whether it's true or not. But here's the point. And the point is this. Galileo did point out something very important, and that is that Earth's gravity tends to make all objects accelerate downwards at the same rate if we're close to Earth's surface. We'll study this in much more detail later in the year, but the bottom line is, in any place you and I are going to go in our lifetimes, if we're not astronauts, gravity is going to make things accelerate at basically the same rate. Now, That rate is something we're going to give a variable letter to, and we're going to make it g. So it's an acceleration. We could call it a, but it's a very specific one. We're going to say little g, and that means technically what it means is the gravitational field strength in the area that we're dealing with. But just for the sake of this unit at least, think of little g as being the acceleration that we associate with gravitation here on Earth, or we could actually transport this to another planet, and the value of g would be different on that planet, but we'd still use the letter g to represent gravitational acceleration. And let's be very clear. In AP Physics, often we deal with things that are falling, and it is up to you to understand that means that they are accelerating at this rate. Now, what is this rate? A lot of you probably have already learned this number, that it is negative 9.8 meters per second squared. This is a number that many of my students come into my class already knowing. They seem kind of proud of the fact that they know this, but I just want to point something out. This is not really what it is. This is g on Earth rounded to two decimal places, to two significant figures. And by the way, significant figures are not something that you have to pay attention to on AP Physics 1. You will never lose points because of how you treated significant figures. So if we round this to 6 significant figures, we get this. Well, I haven't had a student yet come in and say this is what the acceleration of gravity is, and I'm doing this for a very important reason, because College Board, and I very much agree with them, says, you know what, as long as we're rounding it, let's round it to 10. It's so much easier. Okay, let me show you what I mean. Seriously, don't use 9.8. You don't get an added point. They don't go, this kid used 9.8. Let's give him an extra point. They don't. They want you to use this because it just makes it easy. We'd rather you learn physics than learn what g is on Earth to two significant figures. So why is it better to use negative 10 than negative 9.8? I'll show you, and I think you'll agree with me. Okay, try this. All right, a rock is dropped from rest off a building. And it's been falling for 3 seconds. So how fast is it traveling? Well, it's pretty easy if I do it using negative 10. So I'm going to say, well, acceleration times time equals velocity, change in velocity. So that means I just have to multiply g times that's negative 10 times 3. That's negative 30. I think I can do that without my calculator. But try doing it using 9.8, and it's a little bit different. I know some of you might be able to, but most of you can't. I certainly can't. What's 9.8 times 3? I've got no clue. I got to get out my calculator. Oh, it's 29.4. The difference between this and this is trivial. But by using this, it just makes it so much easier to learn physics. And honestly, we often don't even need to do this. We're often just going to leave it as g in AP Physics 1. But let's just try this here. I've got an object moving upwards at 50 meters per second. And it's a cannonball, turns out, okay? It's moving upwards at 50 meters per second. I want to know how fast and which way will it be going 8 seconds later. So I wasn't told what the acceleration is, but I'm to assume, unless I'm told otherwise, that I am here on Earth. And on Earth, g is going to, the acceleration here is going to be g, all right? So, and g is negative 10 is what I'm going to use. You're welcome to use 9.8, but again, you don't get any extra points for that. And so when I solve this, what I'll get is at the final velocity, it's going to end up going negative 30. And so the nice thing about this is it tells me both the speed and the direction, just using this equation we've been working with. But the trick is you had to understand that the acceleration is something that is known here on Earth. And it's worth pointing out that negative 10, you're not obligated to always call it negative 10. Think about this. So Santa Claus drops a toy at the North Pole. It falls down. Where is down? Well, it's towards the center of Earth. It's this way, towards the bottom of my screen, right? Yeah, but what if Santa's evil twin brother, the anti-Santa, broke somebody's toy and dropped it to the South Pole? Well, it still fell towards the center of the Earth, but it fell in the exact opposite direction, right? I don't know, like a gorilla drops a banana at the equator in Uganda. It fell this way. But an orangutan in Sumatra dropped a banana and it fell this way. So the point is, they're not all going the same place. So there's nothing inherently negative about g, so therefore there will be times in this year where I will advocate quite strongly that we choose to make it positive instead of negative. We'll get to it later on, but just understand you don't have to lock into this negative, all right? Because the direction it's going, gravity doesn't always make it go one direction. That's my point. All right, now let's get to something really important here. A very classic kind of problem you're going to get on the AP Physics test is something like this. An object is released from rest at point A. It rolls, say, 6 meters down this incline to point B, and it took it 3 seconds to do that. What is the ball's acceleration? Now, I'm going to show you a couple techniques for doing this and a way to not do this. So let's just start with this. Okay, so just understand, on the AP test, you are usually giving these materials, a hand timer and a ruler, and asked to solve. All right, so here's what we're going to do. I'm going to say, well, the average velocity can be found this way. Average velocity equals the change in position over time. And so it changes position by 6 meters. That's how much it was displaced. It took it 3 seconds. So the average velocity is 2 meters per second. But here's the thing. It wasn't going 2 meters per second here, and it wasn't going 2 meters per second here. It started out at less than 2. It ended up at more than that. This is just the average. This thing's accelerating, so it wasn't traveling 2. It was at one point between here and here. So the trick is, I can do this. I can say, well, an average just means if I have an average of 2 things, I say thing 1 plus thing 2 divided by 2. That gives me its average value, right? 2 people's heights divided by 2 is the average height. So I do the same thing here. So therefore, I know that my average velocity was 2 meters per second, so I can put that here. I know that my initial velocity was 0, so I put 0 here. And now I want to solve for my final velocity. So I'm just saying, what's the average of these 2 velocities? And so you'll see the average velocity is 4 meters per second. Now, I'm just here to tell you, this is a very common setup. And when you have this setup, it's very easy to take the displacement and the time and come up with this average. And all you have to do, as long as it starts from rest, is double the average, and you will get the final velocity. It's a really good trick to have in your toolkit. Now that I know what the final velocity is, I can go ahead and find the acceleration. So now I say, well, acceleration is just v final minus v initial over delta t. And so by solving this, I can see that it's accelerating at 1.3333 meters per second squared. But let me show you something that my students often do wrong. It drives me crazy, okay? They go, all right, well, here's the thing. I can find the velocity by saying 6 divided by 3 is going to give me 2 meters per second. And that's meters over second. And acceleration is meters over seconds over second. So I'm just going to divide this by 3 seconds and get this. But that is not the answer. If you recall, the answer was 1.333, and that is half of it, isn't it? Okay? So this does not work. Don't do it this way. This is a mistake I see made so many times, and it's just embarrassing. So instead, what you're going to do is this. All right, drum roll, please. I'm about to show you something that's really important. The most important equation to know on the AP test is this one right here. Delta x equals 1/2 AT squared. Please memorize it. This is the holy grail equation. This is the one that is going to get you a 5 on the AP test. If I were you, I would seriously consider right now going out and having it tattooed on your body. You need to know this equation to get your 5 on the AP test. Now, there's one thing about it you need to know. Delta x equals 1/2 AT squared works only if the object starts or ends at rest. As long as that's the case, it'll work. So let's look how we would apply it to that previous example, right? So if you recall before, what we did is we said we found the average velocity, then we double it, and then we divided by time, and what we got was 1.33 meters per second squared. But watch what I would do here. I'd say, okay, well, I know how long it fell for. I know how far it went, so that's perfect for this equation. And if I want to find acceleration, I'm just going to say delta x equals 1/2 AT squared. I looked at my tattoo. That's how I knew. Okay, so I'm going to substitute in the delta x was 6 meters. The time was 3 seconds. I have to square 3 seconds here. So what happens then is I get acceleration. I had to multiply by 2 to clear this out. That became 12 meters. I had to square both the 3 and the second, so that's over 9 meters per second squared. And when you solve that, what do you get? You get 1.33 meters per second squared. It's just so easy. And on the AP test, they almost always give you, as tools to do your experiment, a hand timer and a meter stick. So the hand timer and the meter stick, this equation is always your friend. Okay, if you've watched this far, thank you. Why don't you go ahead and stop and go do your homework? All right, but there are a few of you I know who want to ask this question. Mr. Sampson, how did you derive this? So for those of you who want to stick around and see what that is, I'll go ahead and explain it. So here you go. So how do you get delta s equals 1/2 at squared? The best equation in AP Physics is this. Remember that average velocity is just the change in x over time, and average velocity, average anything, is just two things added together divided by 2. And so in this case, the two things are my final velocity and my initial velocity, but in this case, my initial velocity is 0. Remember, this only works if you start it into 0, and this is why. Because since I have this, I can substitute like this. I can say, well, this is delta V. You go, Mr. Sampson, I thought delta always meant final minus initial, not 0 plus final. Yes, but think about this. 0 plus final is the same thing as final minus 0. So this is V final minus V initial, and that's delta V. So therefore, I can get this expression here. Now what happens is I'm going to substitute delta V with AT, and here's why I can do that. Because acceleration is change in velocity over time. So therefore, acceleration times time is delta V. All right. Now what I'm going to do is I'm going to take this equation here, and I'm simply going to substitute delta V with AT, and I get this expression here. But look here, V average is equal to delta x over t, so let's just go ahead and substitute that in there and get this. Now all I have, I'm almost there. Now I just want to get delta x by itself, so it's being divided by t, so what I need to do, I need to multiply by t, so I'm going to have t squared, and then I get this. Boom! As always, thanks for watching. If you like this video, remember, like this video. Consider leaving me a comment. If there's some video you'd like me to make, I'd be happy to do that, or maybe you could just give me some feedback on how to improve. You might want to check the description below to see if there's some links I've included that could help you out. And of course, as always, I would really appreciate it if you would like and subscribe.